Hey everybody, in this video we are going to go over acids and bases, and no pun intended, but we are going to basically scratch the surface of acids and bases. So some of these things are oversimplified and some of these things might not make much sense, but in a future video, chances are your confusions will be clarified. So let's get started. An acid is anything that releases an H+. So let's look at the strong acids and weak acids. And we covered this in a past video, or you might just know this from prior knowledge. But a strong acid is something that when dissolved, so for example, when we dissolve HCl, hydrogen chloride gas, into water, we know that it becomes, well, aqueous because it's dissolved in water. Now, upon entering water and being dissolved, HCl actually dissociates nearly 100%. Or actually, to be more specific, it ionizes. Now, ionization occurs because a molecular substance having a neutral charge becomes two ions, so it's ionized. So this will happen nearly 100%, which means that the reaction will go nearly 100%, which also means that almost all of our HCl aqueous will become H plus and Cl minus upon entering solution. Now, weak acid is basically an acid that does not ionize 100% of the time, so maybe it's like 10%. So that's what a weak acid is. Let's talk about what our strong acids are. These are our strong acids, and basically anything that's not on this list is a weak acid. Now there are some huge exceptions, which we will talk about in a future video, but since we are making this very oversimplified, basically anything that's not on this list is a weak acid. So just bear with me, and let's look at some examples of weak acids. Do you guys know how to name this? What's NO2 minus? That's nitrite. So I think this acid, HNO2, is called nitrous acid because the ite becomes an is. So are your memories of naming acids coming back? Well, mine's is sure coming back. Now this one is phosphoric acid because phosphate, 8, becomes ic with a special name change in the middle, which you could review by looking at how to name acids, which is one of my videos. HCH3COO. Now you're used to seeing CH3COOH, or maybe the condensed form C2H4O2. All of these mean the same thing. They're acetic acid. Acetic acid's a part of the weak acid list, so it's a weak acid. Hydrofluoric acid is also a weak acid. And whoa, water? How is water an acid? Well, it technically can be an acid because anything that releases an H plus is technically an acid. So let's see how H2O can release an H plus. Well, can't it do this? Can it just ionize? Well, yeah, it does do that, and look at that, it releases an H+. So we could technically classify H2O as a weak acid, although that is typically not the case. But you could. Now let's talk about bases. Bases are a bit more complicated. It's anything that releases an OH-, or it's something that accepts an H+. So notice how an acid releases an H+, a base accepts an H+. They do the opposite things. You gotta also know that bases release OH- upon contact with water, or upon dissolving to be more specific. So let's look at our strong and weak bases. So basically, no pun intended again, just kidding, pun intended, everything that ends with an OH- will be a strong base because, well, anything that ends with an OH-, or in other words, it has to be a salt with its anion being hydroxide. So for example, let's do magnesium hydroxide. we know from our solubility rules that this is super insoluble. So it's insoluble, but the amount that dissolves, so this tiny amount of magnesium hydroxide that dissolves, so we'll put an aqueous there, that little amount that kind of just dissolves in water, all of that will dissociate, and in this case I use the word dissociate because upon contact with water, we already know that magnesium hydroxide is composed of anions and cations, so all that's happening is that they're being separated, and there's no sort of ionization going on where things are gaining or losing charges because the charges were there in the first place because this is a salt. So upon dissolving, an MgOH2 that dissolves will almost nearly 100% of the time split into that and two OHs. And because it splits upon dissolving nearly 100% of the time, we call that a strong base. 100% dissociation or ionization, depending on what we're looking at. So anything that ends with an OH, call that a strong base. Now, what's a weak base? Well, basically anything that's not on this list. But, of course, it gets complicated. So this is an oversimplification. And, of course, there are other strong bases that don't end with an OH, but don't worry about that for now. So one weak base is NH3, ammonia. Now, how is water a weak base and a weak acid? Well, how does H2O possibly produce OH minus? Well, let's look at that. H plus plus OH minus. Look at that. Water produced OH minus. So it can technically be a weak base. And of course, we have a lot more weak bases, which we won't worry about. Now, let's now talk about neutralization reactions. We talked about these all the way in the beginning, 2.13. That's the video if you want to check it out. But if you know what you're doing, and if you know what neutralization reactions are, by the way, they happen between acids and bases, let's move on. So, I want to introduce a concept called equivalence. An equivalence, it's a number of hydroxide ions that one molecule of acid can react with. So let's take a look at this example. HCl. Let's just say we have one molecule of HCl. One molecule of HCl contains one H plus. And this one H plus can react with exactly one OH minus. So since I said that that was one molecule of HCl, this should be one molecule of OH. Because one molecule of H plus one molecule of OH makes water. And why is this an acid-base reaction? Well, if you remember, neutralization reactions occur when the H plus is transferred. So in this case, all that happens is that this H plus basically transfers itself to this OH to create water. So this in itself is a neutralization reaction. Wow, right? Pretty neat. Now, let's look at H2SO4. Let's just say we have a mole of this stuff. A mole of H2SO4, sulfuric acid, will have 2 moles of H+. 2 moles of H+ can react with exactly 2 moles of OH-, because this reaction is in a 1-to-1 ratio. And look at that, 2 moles of H+ mixed with 2 moles of OH- becomes 2H2O. So, in this case, we have to think about what we're looking at. We're looking at the equivalence of this. Remember, equivalence is the number of OH- that one molecule of acid can react with. So in this case, one molecule of acid, so let's just say this is molecules again to simplify things. One molecule of H2SO4 has 2 molecules of two molecules of H+, and 2 molecules of H+ can react with exactly 2 molecules of OH- according to the reaction. Remember, we could read this reaction in terms of moles and molecules. So, because of that, that means that H2SO4 or one molecule of H2SO4, has an equivalence of 2 because it can react with 2 OH minuses since it has 2 H pluses. Let's take a look at the second definition. We got also define equivalence as a number of H pluses that one molecule of base can react with. So let's look at NaOH. NaOH has one molecule of OH minus, which reacts with exactly one molecule of H plus. So NaOH has one equivalence. Now what about barium hydroxide? This has two equivalences since two OHs react with exactly two H pluses. So let's go back and write our answers. So HCl has one equivalence, H2SO4 has two equivalences, and we have them right here. And now let's move on to the next important topic, probably more important than the last topic, but who am I to say that things are important or not? Let's talk about normality. Normality is represented by the letter N. Normality is equal to the molarity, and we're talking about acids and bases here, by the way, times the number of equivalences. So let's find the normality for 6 molar hydrochloric acid. That's just the molarity of the acid times the number of equivalences. While HCl has one H plus, which can react with exactly one OH minus. So since HCl reacts with one OH minus, it has one equivalence. So that's 1. And 6 times 1 is 6. So the normality of HCl in this case is 6. Now let's talk about 6 molar of H3PO4 phosphoric acid. The number of equivalences for H3PO4 is actually 3, because it can release up to 3 H pluses, since you could look at that and say that there can be at most 3 H pluses that can be released from this phosphoric acid. And of course, if you release 3, you're left with a phosphate ion. And since 3 H pluses can react with 3 OH minuses, then the equivalence of phosphoric acid is 3. So multiply its molarity by its equivalence to get 18 for its normality. Now the reason why I'm emphasizing that you should look at the number of OHs that the acid reacts with, there is a reason for that. And the reason is, let's take a look at CH3COOH. Now, we know that CH3COOH is actually a monoprotic acid. And that simply means it releases one H plus, which reacts with exactly one OH minus, which means the equivalence of acetic acid is 1. Now, if you decided to try to take a shortcut and count the number of H's to determine your equivalence, there are times when that doesn't work. Because if you count the number of H's, we would say there were 4 equivalences, but that's absolutely not right. Because these 3 H's actually don't get turned into H pluses. Now you might be wondering, why not? Well, in a future video, I will talk about that. But something cool to know is that acetic acid is a monoprotic acid that reacts with exactly 1 OH for every 1 acetic acid. Now, let's talk about how to completely neutralize something. Now, to completely neutralize something, basically, you have to have a neutralization reaction that goes all the way, or when all the reactants are consumed. So this is when all reactants are consumed. Now, there are some special variations of neutralization, but in this case, I want you to consider neutralization as when all the reactants are consumed. So let's take a look at this example, and I'll show you a shortcut using normality. 5 liters of 6 molar of phosphoric acid, so we have that. How much 2 molar of barium hydroxide do we need to neutralize this stuff completely? So in other words, we need to react enough of this so that all of this gets reacted with. So what I want to do is write the reaction for this. That's the reaction. And I balanced it, of course, because that's super important. So what I want to do first is find, well, how many moles of H3PO4 do I have? So to do that, we know that to get the number of moles, we take the molarity and multiply it by the volume. And note that the volume should be in liters because molarity is moles per liters. And you multiply by liters, the liters cancel out and you're left with moles. So 5 liters times 6 molar of phosphoric acid is just 30 moles of phosphoric acid. Now, if we have 30 moles of phosphoric acid, how much barium hydroxide, or how many moles of it do we need to make this reaction successful? Well, according to this reaction, for every 2 moles of phosphoric acid, we need 3 moles of barium hydroxide. So that's our conversion to tell us how many moles of barium hydroxide is needed to completely react with all that. And this reaction helps us do that. And you should also notice that these two cancel out when you do that, leaving 45 moles of barium hydroxide. It's kind of a lot. Now, we have to go backwards because we want the amount of volume. How much of this solution do we need? So we need volume. And we know that molarity times volume, in liters preferably, actually it has to be, will equal moles. So we have 45 moles of barium hydroxide equal an unknown volume times the molarity of barium hydroxide, which is 2. And we do some math and we get that we need 45 over 2 liters of barium hydroxide to completely react with all this stuff. Now you could do it that way. That's the legit way. Now this is also a legit way. It's this cool formula that is very similar to the dilution formula, which was M1V1 equals M2V2. It looks really similar, but in this case, we are looking at the normality of the acid times the volume of the acid is equal to the normality of the base times the volume of the base. So preferably that should be in liters, that should be in liters, that should be in normality, and that should be in normality. Now to tell you the truth, if you use this equation, you actually don't need to have the volume as liters. It could literally be milliliters, it could be gallons, literally anything. But to keep it simple, just use liters so you don't confuse yourself. But it's nice to know that you can use anything for those two, because to tell you the truth, they actually cancel out on both sides of the equation, which means that as long as both sides have the same units, it doesn't really matter. So let's just focus on liters. Let's set this equation up. The normality of A, well, A is our acid, so this is our acid. The normality of this acid is, well, 6 molar of H3PO4 times 3 equivalences to get 18N, which is the normality of our acid, and we have 5 liters of it, and we set it equal to the normality of the base. So normality of the base is the molarity of the base times the number of equivalences. So the molarity is 2 molar, and the number of equivalences is 2. So 2 molar times 2. And we don't know how much volume there is, so we kind of got to solve that. And doing some math, we get that VB is going to be equal to 45 over 2 liters, the same as the answer we got down here. So look at that. This equation makes things super easy. It's something worth memorizing, to be honest. Now, the next thing I want to do is kind of prove why this formula works. NAVA equals NBVB. So, if we think about this, Na is simply the molarity of A times the number of equivalences, or the number of OH minuses it reacts with. And in this case, we could either look at moles or molecules, doesn't really matter. It's just that for every 1 mole of, H plus. If you react with 1 mole of OH minus, well, you have one equivalence. You could say 1 molecule of H plus and reacts with 1 molecule of OH minus to form 1 molecule of water, which is one equivalence. It doesn't really matter if you use moles or molecules. In this case, we'll use moles. So we will drag the VA down, and this is equal to, we basically have to split this definition up because we know that N is equal to M times the number of equivalences. And for a base, the number of equivalences for a base is the number of H pluses it reacts with. And of course, we just drag that down. So we kind of expanded this equation. Now let's expand it even further. The molarity of A is just the moles of A per liter. The number of OH minus it reacts with, well, it's the number of moles of OH minus reacted for every mole of acid. So if we have 1 mole of HCl, we know it'll react with exactly 1 mole of OH minus since it has 1 H plus in it. So that's where the logic comes from, and we're multiplying by VA. And we do the same for MB by expanding it even further to its simplest definition. And then we kind of just say the number of moles of H plus reacted per mole of the base and times VB. Now, you should notice that things start canceling out, these two and these two. And you should also notice that the liters also cancel out because volume on the top, volume on the bottom, they cancel out. And you're left with the moles of OH minus reacted is equal to the moles of H plus reacted. Well, isn't that what this reaction says? The moles of H plus and the moles of OH minus are the same in a 1-to-1 ratio. So this equation that we just derived is true. So the moles of H plus reacted is equal to the moles of OH minus reacted. So that is kind of an explanation why this formula at the beginning works. It's simply because the moles of OH minus reacted is equal to the moles of H plus reacted. So yeah. So let's now look at something called equivalent weight really quickly. The equivalent weight is either the weight of the acid required to neutralize 1 mole of OH minus, or the weight of the base needed to neutralize 1 mole of H plus. And the weight that we're referring to is usually measured in grams. Now let's do an example to see how this works. Let's find the equivalent weight for sulfuric acid, which has a molar mass of 98.08 grams per mole. So we know that 1 mole of H2SO4 has 2 equivalences, which means that it can react with 2 OH minuses at most, since it has 2 H pluses. So we know that when they react together, they of course form 2 moles of water. But that's not the important part here. Well, it kind of is, because when we write the reaction out, we can see that this is a neutralization reaction where these 2 H pluses react with the 2 OH minuses to form 2 waters, leaving behind the sulfate anion. And we can actually use this reaction to help us out. So we know that 1 mole of H2SO4 will be neutralized by 2 moles of OH minus. And when I say neutralized, I mean neutralized completely, as in all the H pluses are gone from the original acid. So in this case, we want to find how much H2SO4 is required to react or neutralize 1 mole of OH minus. So I start off with 1 mole of OH minus that I want to neutralize, and according to this reaction, for every 2 moles of OH minus I want to neutralize, I need 1 mole of H2SO4 to do that. And we can just multiply this by the molar mass to cancel out the moles of H2SO4, leaving behind, well, the grams of H2SO4, once we realize that the moles of OH also cancel out. So you have a canceling out effect, and you end up with 49.04 grams of H2SO4. And this is also half a mole of H2SO4, by the way. So you might have noticed a little shortcut. If I said that we have to neutralize 1 mole of OH minus. And if we know that 1 mole of H2SO4 can neutralize 2 moles of OH minus, then if we want to neutralize just 1 mole of OH minus, then we wouldn't need 1 mole of H2SO4, we would need half a mole of H2SO4, since we're just scaling everything down, because if 1 mole of H2SO4 reacts with 2 moles of OH minus, then we know that half a mole of H2SO4 will react with half as much, or 1 mole of OH minus. So you could have just taken this 1/2 mole of H2SO4 and converted it into grams. So there are a lot of ways to do this, but that's the idea. And let's move on to one last topic. It's the equivalence point. Notice how we have a lot of words that have the word equivalence in them. That means that it's a really important concept. So the equivalence point is when the moles of OH minus equals the moles of H plus. Now, it's a little bit more complicated than that, but just think of it like that for now. And it looks eerily similar to how we proved this formula over here, using the idea that the moles of OH minus reacted is equal to the moles of H plus reacted. But it's slightly different, as you will see. But don't worry about that. Let's just read on and see what it is. So, obviously, when we look at the fact that 1 mole of OH and 1 mole of H plus are equal, we can think of them as neutralizing each other to form, well, water. So, in this case, the first equivalence point, so they're different stages, I guess, depending on what we're looking at. So the first equivalence point is when 1 round of H plus is neutralized. Now, what does 1 round mean? Well, it just means that if you have an acid, then we're only looking at one of its H pluses. And since HCl has only one H plus, that's the only one we're looking at. So we can say that hydrochloric acid has 1 round of H plus. Well, primarily because it has only one, and that's what we call a monoprotic acid. And let's clarify this name a little bit. I think I did this before. Mono means one, protic. Now, why are we talking about protons if we're talking about H pluses? Well, an H plus is actually a proton. So if we remember, the most common isotope for H is a hydrogen having just one proton and no neutrons. So it's, I think that's the mass number. The mass number will also be 1 because the number of protons, which is 1, plus the number of neutrons, which is 0, is equal to 1. So if you think about this, we can draw NH, which is just one proton, and of course it has to have an electron there, because we know that overall an H has to be neutral, so it has to have one electron, primarily because it has one proton, and it has no neutrons, as you can see. Now, if it's H+, which means that it lost an electron, all we have left is a proton. So essentially, an H+ is a proton. So hopefully that made sense. And let's move on. So the second equivalence point is when the second round of H+ is neutralized. So notice how HCl doesn't have a second round because it only has one H+. Now, what if you have more than one H+, like H2SO4? Well, you get to have a second equivalence point as well as a first. So we call H2SO4 a diprotic acid because it has two H pluses that it could give up. And you can also think of this as two equivalences. So we can draw the first round being neutralized. So the first round of H plus can be neutralized by 1 mole of OH minus. Since the first round, we only need to neutralize one of its H pluses, or 1 mole of its H pluses. So we only need 1 mole of OH minus to do that. And as we can see, this reacts and 1 H plus is transferred, and you end up getting HSO4 minus plus H2O. And this is the first equivalence point because the first round of H plus was neutralized and kind of taken away from this H2SO4, leaving an HSO4 minus. So let's take a look at what we can do to neutralize the second round of H pluses. So that's the last one for the the HSO4 minus there. So this is the second equivalence. So to neutralize this second H plus, which is just one H plus once again, we need 1 mole of OH minus to do that. And once they react, the H plus is transferred and we end up getting these two. And when all of basically this stuff becomes this stuff, then the second equivalent point or the second equivalence point is reached because the second round of H plus is completely gone. So to completely get rid of 1 mole of H pluses, which is a part of the HSO4 minus, you need exactly 1 mole of OH minus to do that. Any less than that will not completely neutralize the 1 mole of H plus that's present in this compound, which means that you will not have reached the second equivalence point unless you added that 1 mole of OH minus to completely neutralize that 1 mole of HSO4 minus. Now, do you guys know what HSO4 minus is? Well, we can call this hydrogen sulfate, or we can call this bisulfate. So last but not least, we have our third equivalence point. That's only when you have acids that have 3 or more H pluses. So either a triprotic acid or, things that have more than 3 H pluses. And yeah, so it's the same idea. And an example of a triprotic acid is H3PO4 minus. And the third equivalence point for this acid is, when its final H plus gets released. So it will have its final H plus when it's HPO42 minus. And then it only needs 1 mole of OH minus to react with it, forming your final compounds, phosphate and water. So yeah, so we will discuss this concept in a future video, in video 12.10. That's really far away. So notice how all these things are going to help you build up to the more complicated discussions and the more detailed discussions that will occur in future videos. So this was kind of like a platform for you to jump off of, and I hope you learned a lot and have a nice day.